Good morning, Prof. and fellow classmates. Today, we will be presenting on the topic of Markov matrices. So what are Markov matrices? They are square matrices that determines the transition of a Markov chain. And a Markov chain is a stochastic process that describes a sequence of possible events in which the probability of each event depends only on the state attained in the previous event. The row or column vectors in a Markov matrix contains the transition probabilities of one state to another, and they are conditional probabilities represented in linear algebra. The following are some properties of the Markov matrix. Firstly, the elements in the vector are non-negative real numbers that sum to 1. Secondly, there is the left Markov matrix where elements in the column vector sum to 1, and the right Markov matrix where elements in the row vector sum to 1. We will be using the left Markov matrix for the rest of this presentation. So, let P be a S by S Markov matrix. It describes the Markov chain over a finite state space S with a cardinality S. The state space of a Markov chain is the set of values that could occur in each step. So in a 2x2 matrix, there are only two possible states. Given a Rs vector space, the matrix has a dimension of S. So any basis of Rs has S vectors in it. Therefore, the Markov matrix has a cardinality of S. The rows of P Markov matrix represents the next state, and the columns of P represents the current state. For example, P12 gives the probability of transitioning to state 1 given the current state of 2. So to generalize, the conditional probability of J given I is represented as Pij in the Markov matrix. Once again, the sum of transition probabilities from a state to all other states must be 1. And since we are working with left Markov matrices, the column vector sums to 1. Finally, the main diagonal of the Markov matrix gives the probability of remaining in the current state.
Hence, we will get 3 out of 5 and 2 out of 5 respectively. After solving the first part of the question, we can see how we might solve for 2 days or 3 days after day 0. We will simply multiply the resultant matrix by our Markov matrix another 1 or 2 times respectively. However, what if we have n days to consider? In this case,
So what is a Markov chain? A Markov chain is a sequence of possible events in which the probability of the next event depends only on the state attained in the current event. This meaningless property is known as the Markov property, where predictions can be made regarding future outcomes based solely on its present state. Markov process can exist in a discrete or continuous state space. Additionally, it can also exist on a discrete or continuous time. For our presentation, we will be working with discrete time and state space. Let's have a small example with regards to the meaningless property. Given a bowl containing 2 red balls and 1 green ball, one ball was drawn yesterday, one will be drawn today, and one more will be drawn tomorrow, and each ball is replaced after each draw. What is the probability of drawing a green ball tomorrow given that a red ball is drawn today? With 3 balls drawn over a span of 3 days, there are 3 different possible outcomes as laid out in the table. As you can see, the probability of drawing a red and green ball remains constant throughout the 3 days. This is the meaningless property where the probability of moving to the next state depends only on the present state and not on the previous states.
with an introduction to the concepts and characteristics of the Markov matrix, we will now attempt to apply the Markov chain to a system of 2 states. Our example will answer the question of whether it will continue to rain. Understandably, there is a multitude of factors that go into determining and predicting weather conditions. However, we will simplify our problem to only concern ourselves with 2 states. Our problem can be split up into 3 parts as follows. Suppose it is raining on day 0 today. What would be the probability that it is raining and not raining after 1 day? Similarly, what would be the probability after n days, and lastly, after an infinite number of days? Here, we first begin with a probability table of the various states. To put it simply, 0.6 is the probability that it will continue to rain given that it is currently raining. 0.4 is currently not raining for 0.8 and 0.2, with the probability that it will rain and not rain respectively. We can also further visualize this in a state diagram. showing the probabilities of the possible state changes from a given starting state. We can extract this visualization and apply it into a Markov matrix for us to solve the problem. So, let us now approach the first question, finding the probability that it is raining and not raining after one day. We first construct a simple column vector, denoting the possible states at day 0. 1 signifies that it is raining on day 0 and 0 signifies that it is not raining. Now we can simply perform a matrix multiplication of the Markov matrix by our constructed column vector to give us the probabilities of raining and not raining on day 1. Hence, we will get 3 out of 5 and 2 out of 5 respectively. After solving the first part of the question, we can see how we might solve for 2 days or 3 days after day 0. We will simply multiply the resultant matrix by our Markov matrix another 1 or 2 times respectively. However, what if we have n days to consider? In this case, we will have to solve for the Markov matrix to the power of n. This problem can easily be simplified using eigenvalue decomposition, which in general allows for good algorithmic computation time as well. Below, we perform EVD on the Markov matrix and expand it out to find its diagonal matrix. Simplifying, we get a matrix that varies with n, allowing us to generalize the solution to this problem. Now that we are ready to tackle the final part of our problem, infinity. This is conceptually simple. We just raise the Markov matrix to the power of infinity, just as we took the power of n for n days. But this computationally doesn't look as simple anymore, does it? Well, not really. In fact, we can make use of EVD that we obtained from the second part to aid us in finding the solution. Here, we can substitute n equals to infinity, which gives us a convergent solution where negative 1 over 5 will eventually tend to 0 as n tends to infinity. This way, we can see that the solution is a simple 1 over 3 multiplied by our column vector. As such, we have shown how Markov matrices might be involved in the calculation of probabilities for state transitions.
Now, let's discuss some properties of Markov chains that are notable in real-life examples. The 3 properties that we'll be discussing here are reducibility, periodicity, and ergodicity. Reducibility. A Markov chain is said to be irreducible if it is possible to get to a state J from any other state I. On the other hand, if it's not possible to get from one state to another, the Markov chain is said to be reducible. In this matrix from earlier, we can visualize that the probability of reaching an end state from any initial state is non-zero, which means that the associative Markov chain is said to be irreducible. Second, we have periodicity. A state in a Markov chain is periodic if the chain can return to the same state at multiples of an integer k, where k is greater than 1. Periodicity usually serves as a measure of predictability of an irreducible Markov chain. This means that if a Markov chain is periodic, there is some degree of predictability in its states. The period of an irreducible Markov chain, such as the one we saw earlier, is important because it tells us about the long-term dynamics of the chain and how the states might evolve over time. Lastly, we have ergodicity. A state is said to be ergodic if it is aperiodic and the probability of it recurring is non-zero. We see that the chain is aperiodic since the occurrence of states does not follow a fixed pattern. Also, from an earlier result, we can see that the probability of a recurrence of either state is greater than 0 for when n is equal to infinity. This means that the probability of a state occurring again is non-zero. So as such, the matrix in this example can be said to be ergodic.
With that, we've come to the end of our presentation, and we hope you enjoyed it.